We've seen how to solve certain types of oblique triangles when we're given certain pieces of information. If we're able to use the law of sines, then that must mean that we were able to fill in a complete ratio, either sine of angle A over A, or the same thing with B or C. But there were certain situations where we were given information, let's say 3 sides of the triangle, where we weren't able to solve using the law of sines because I wouldn't have a full ratio. Or sometimes I'm given 2 sides with the angle right in between them, at which point I still wouldn't be able to find a complete ratio. So in those 2 situations, either side, 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 or side, angle, side, we can now use a new formula referred to as the law of cosines. So let's take a look at the derivation. We have a triangle ABC where I've dropped the height right here straight down from angle B. And notice that that formed a right triangle. It formed 2 right triangles, in fact, one on the left side of H and one on the right side of H. And so in order to derive this law of sines, we're going to label this bottom piece right here of the right triangle on the left, side X. Now we're going to look at a few trigonometric relationships in that triangle now. So we're looking at this triangle for now on the left side. Okay, so we know that cosine of angle A is going to equal the adjacent side of X over the hypotenuse of C. So notice if we multiply both sides by C, that means that that base of X is actually C times cosine of A. So that means that we could actually come down here and realize that this base is C cosine of A. And the nice part about that is that now those are in terms of the angles and sides that we were given in the problem, because most of the time we're not given the height. But we need the height in order to derive this. So let's go ahead and take a look at another relationship, which would be sine. Let's take a look at sine of angle A. Well, sine of angle A is the opposite side over the hypotenuse. So if I multiply both sides by H, or by C rather, I get that H is equal to C sine A. And so this should make sense because notice that cosine of A, if I'm starting at, let's say, the origin, cosine of A is the X coordinate, sine of A is the Y coordinate. And so if the radius or the hypotenuse is C, then I just simply multiply the X coordinate of cosine times C, and I multiply the Y coordinate of sine A also times C. All right, well, if the entire base is considered B, then that would mean that this piece right over here is going to be B minus that length of C cosine A. And now we should realize that every piece of this diagram is in terms of the sides A, B, and C, as well as the angles A, B, and C. So we're going to focus now on this triangle right over here. And we're going to see the relationship here by taking using the Pythagorean theorem to show that there's a relationship between some of these sides here. So the Pythagorean theorem says to take C times sine of A squared and add to it B minus C cosine A squared, and that should be equal to A squared. Okay, well, if we expand this, then let's just put the A squared on the left side. So A squared equals, and now we're going to expand to get C squared sine squared A. We know that this is a binomial, so I'm going to be writing B minus C cosine A times another B minus C cosine A, which gives me B squared minus 2BC cosine of angle A plus, and now I square C cosine A to get C squared cosine squared of A. And that technically is a formula that relates all of that information. But we're going to look at a couple of terms here and realize that this term and this term both have a common c squared. So why don't we rewrite this then as a squared equals b squared, which is right here, plus, but then why don't we factor out the c squared from those two terms, and notice that I'm left with sine squared a plus cosine squared a. And finally, minus 2bc cosine a, which is the last term. But keep in mind that sine squared a plus cosine squared a is the Pythagorean theorem. That's 1. So notice that we have a formula, a squared is equal to b squared plus c squared minus 2bc times cosine of angle A. And what we have here is referred to as the law of cosines. Now this is definitely a bit more intricate than the law of sines, but what the benefit of this is that if we're given two sides, let's say B and C, which is here and here, and we're given the angle in between them, which is right here, then I should be able to find the other side of the triangle, even if I'm given side, angle, side. But notice that I just labeled these sides arbitrarily. I labeled angle A down here when I could have called it angle C. And I labeled this angle B when I could have called it angle A. And I labeled this angle C when I could have labeled it A or B or whatever it is. And so since these were labeled arbitrarily, it turns out that I have two other forms of the law of cosines. So the law of cosines here could also be written in two other forms. First form is to solve for b squared. What if we have b squared equals? So now instead of solving for side A, maybe we solve for side B, and if we did that, it would be the exact same format. A squared minus c squared plus c squared minus 2ac times cosine of the angle between them. So a few ways to remember this. If you're dealing with A and C, then you're taking cosine of the other value. Another way to look at this is, if I'm dealing with angle B, then the opposite side is solving for side B. And we could also have another one where we have c squared, maybe we solve for c squared, and that's equal to a squared plus b squared. And look at how that resembles the Pythagorean theorem. The only difference now is that we have 2ab times cosine of angle C. All three of these are just different forms of the law of cosines. And so if we're given all three sides, we could find the last angle. So if we're given A, B, and C, we'd be able to plug all of these quantities in, and the only unknown would be angle A. Or if we're given A and C, along with the angle between them, then we're able to find the other missing side. And so using these laws of cosines for either side, 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 or side, angle, side, we now have two different formulas, the law of sines and the law of cosines, to be able to solve for any missing information. So let's do an example. In this triangle, we could go ahead and try to use the law of sines by saying that sine of 42.3 degrees over side A is equal to sine of angle B, which we don't know, over 12.9. And notice that that's also equal to sine of angle C, which we also don't know, over 15.4. And so what you should recognize here is we don't have a full ratio filled in. We don't have angle A with its opposite side. We don't have angle B, we don't have angle C, and there's no way with only one angle to find angle B and angle C. And so this is showing us why we're not able to use the law of sines here. So what we need to do instead is recognize that because we're given angle A, we're going to start with the formula for the law of cosines that starts with A squared, which equals B squared plus C squared minus 2 times BC cosine of angle A. And notice why this is beneficial, because we know what side B is, we know what side C is, and we know what angle A is. So all this is a matter of plugging in our values and giving us A squared is equal to 12.9 squared plus 15.4 squared minus 2 times 12.9 times 15.4 times cosine of angle A, which is 42.3 degrees. So although this is a much longer formula normally to think of instead of the law of sines, it automatically isolates the side that we're going to need, which is side A. And so notice that we could just continue to simplify and get our result. Okay. So if we simplify each of these, we get 12.9 squared is 166.41. So 166.41 plus, and now we got 15.4 squared, so 15.4 squared is 237.16. Okay, minus 2 times 12.9 times 15.4 is 397.32. And finally, times what cosine of 42.3 is, 42.3 degrees. We need to make sure that we're in degrees when we're using our calculator. And so we've got cosine of 42.3 degrees is about 0.73963. And notice that all of that is solving for A squared. And so if we now combine all of those using our calculator here, we get A squared is equal to approximately 109.7. And now in order to solve for A, we take the square root. We know that it's a side length, so we only have to worry about the positive result. So we know that side A is going to be equal to 10.47 meters. And so although we were given side angle side, the law of cosines allowed us to find this next side. And now we realize that we are able to use the law of sines. Because notice, I can now come up here to A and plug in 10.47. So you should never have to use the law of cosines more than one time per problem, because now at this point, we can set up the law of sines using B and A. And this would allow me to find angle B. Okay, so if we cross multiply, we get the sine of angle B is equal to 12.9 times sine of 42.3. And that's still divided by 10.47. All right, so sine of angle B is equal to that quantity. So if we apply or use our calculator and find the inverse, we get that angle B is equal to 56.0 degrees. But notice that it could also be the supplementary angle. So we have to also say B2 is equal to, and if I subtract that from 180, I get 124 degrees. Every time you get two angles or two potential different triangles, you have to really think a little bit about whether or not that's possible. If B was equal to 124 degrees, then that would mean side B would have to be the longest side because 124 degrees would be the biggest angle. But if you look up here, B is not the biggest side. C should be the largest side. So this is why it was a good idea to use the law of sines with angle B instead of with angle C. Because if we used it with angle C, we'd know that that would have to be the largest angle, and then we wouldn't know which triangle we were actually referring to. So when you use the law of sines after using the law of cosines here, definitely make sure to use the angle that's not going to be the largest angle. So we know that this is not a possibility. And so now in order to find angle C, the easiest way to do so is just to realize that angle C is 180 degrees minus the sum of the other two angles. So 42.3 degrees plus 56.0 degrees. Okay, so that gives me 180 minus 98.3 degrees. So when I subtract those, I find that angle C is 81.7 degrees, which if you look at all of the angle measurements is still the largest of the three angles, which makes sense because it's opposite the largest side. So once we use the law of cosines the first time in order to find the missing piece of information, we can then resort to using the law of sines to answer the rest of our question. Now in this next example, we're given all three sides. So we really have the three different options for the law of cosines. Although it technically doesn't matter which side or which of the three angles we solve for first, it's typically best practice to realize that the largest side is 21.1 feet. So I'm going to solve for the largest angle first, because then I'll be guaranteed that if the cosine value is negative, I know the answer is obtuse. If the cosine value is positive, I know it's an acute angle. So that's why we're going to start the equation by saying c squared equals, and a squared plus b squared minus 2ab cosine of angle C. So notice that this is the quantity that we're going to try to isolate by plugging in all of our A, B, and C values. Okay. So let's plug in 21.1 for C. We plug in 9.47 for A. We plug in 15.9 for B. And now we get 2 times 9.47 times 15.9. And the only unknown now is going to be cosine of angle C. So let's just think about how we need to approach this problem. We first of all are going to have to subtract, so we're going to take 21.1 squared. We're going to have to subtract 9.47 squared to the other side. We'll subtract 15.9 squared to the other side. And in order to isolate, since this is gone and this is gone, in order to isolate cosine of C, we'll have to divide by all of that coefficient. So that becomes 2 times, or rather negative 2 times 9.47 times 15.9. And the result of that on your calculator is what the value of cosine of angle C is going to equal. So we should see that cosine of C is equal to the negative of 0.34, 109, 402. Okay, so we get that, but just by evaluating each of these on our calculator. And notice that not only is that between 0 and or negative 1 and 1, which is great, but what we recognize is that because this is negative, I see that cosine is negative in quadrant 2. So when I calculate cosine inverse of that quantity, my answer should become an obtuse angle. So I know that angle C is 109.9 degrees. And so this is why solving for the largest angle first is good, because if it's acute, then the positive value would show me that. But if it's obtuse, then I would possibly get a negative result as well. And so this is what we notice here. So now that we have angle C, we can now just use the law of sines in order to solve the rest. So let's set up maybe sine of angle B over side B, which is 15.9, is equal to sine of angle C, which we just found is 109.9 degrees, over side C, which is 21.1. So we know to isolate sine B, we're just multiplying by 15.9 on both sides, which gives me 15.9 times sine of 109.9 degrees over 21.1. And therefore, when I calculate the inverse of that quantity, we see that angle B should be equal to 45.1 degrees. Okay, and there is angle B. And so now to find angle A, since we already have two angles, that's where we could just say that angle A is 180 degrees minus the sum of each of those other two. So we have 45.1 degrees plus 109.9 degrees. And when we subtract those, we find out that, that angle A is going to be equal to 25.0 degrees. So again, we have two different scenarios where we could use the law of cosines. We either use the law of cosines when we're given side angle side, which is exactly what we see here, because we would notice that with some given angle of 42 degrees, okay, if this is angle A, at 42.3 degrees, then we're given side B, which would be 12.9, and we're given side C, which is longer at 15.4. So notice that since we're missing this opposite side over here, then we must have side angle side, and that's why we had to use the law of cosines. So notice that once we used the law of cosines, we could then go back to use the law of sines in order to find the rest. But what if we're given three sides? If we're given three sides, then we definitely want to make sure that we're solving for the largest angle first, which we know is opposite the largest side, okay? Let's go and write that out, so that's the largest side. And once we did that, after we used the law of cosines the first time, that's where we again resort to using the law of sines and then find the last angle using the angle sum property. Now that we've already used one area formula that involved sine, we're now going to find the area using another formula that referred to as the Heron's area formula. Now the proof for this is much more long and arduous, so we're going to forego the proof, but we are going to show that the area is going to be equal to the square root of S times S minus side A times S minus side B times S minus side C. But notice that that would have to imply that S is some particular quantity. Now we refer to S as the semi-perimeter. It's actually half of the perimeter of the circle. Semi-perimeter. And so in order to find the perimeter of the triangle, we have A plus B plus C, which implies that S is half of that perimeter. And so this is the formula that we can use in order to find the area of a triangle. And it seems kind of peculiar, but notice that all we need are the perimeter and each of the sides, and based on that, we could directly find what the area of a triangle is. So in this example, we'd like to use a couple of our formulas. Our more standard formula for finding the area of a triangle is 1/2 the base times the height. Now this is obviously only possible if we're given the height. But if we're not actually given the height of that triangle, then notice that we're going to have to resort to something else. But in this case, we are given the height just to be able to use this formula. And so we have that area is equal to 1/2 the base, which is 16, times the height, which is 3√3. And so notice that in this problem, 1/2 times 16 is 3, or I'm sorry, 1/2 times 16 is 8, times 3√3 gives me 24√3. So it's a very simple and straightforward problem to find the area using this formula. But let's assume that we weren't actually given the height of 3√3. Instead, we would have to first find S, which is the semiperimeter. So we'd have to find half of 6 plus 14 plus 16. Well, 6 plus 14 is 20. Add 16, you get 36. So half of 36 is 18. So from Heron's area formula, we know that area is equal to the square root of S, which is 18, times 18 minus 6, times 18 minus 14, times 18 minus 16. So basically, each of the differences between the semiperimeter and the length of each side. So that gives me A is equal to the square root of 18 times 12 times 4 times 2. Now, if I were to multiply that all out, that would be a really big number. Okay. More specifically, it would be 18 times 12 times 4 times 2, which is 1,728. Notice that I don't want to have to simplify that by factoring that down and finding the possible roots. So instead, what I'm going to do in here is deal with each of the individual factors and break this down. So I'm going to find A is equal to the square root of, and now let's take a look at 18. 18 is 9 times 2, or 3 times 3 times 2. And then we go to 12. 12 is 6 times 2, or 3 times 2 times 2. And now we go to 4. 4 is 2 times 2. And finally times our last 2. Now, the reason why we did this is because now we can start taking out these pairs of factors, since the square root of 9 equals 3, the square root of 2 is equal to 2, or square root of 4 rather, the square root of another 4 is equal to 2, and notice how I have another factor of 2 that can pull out. So we're left with the area is equal to 3 times 2 times 2 times 2 times the square root of 3, which is the only quantity that we didn't didn't have a pair, which now means that this simplifies to 24√3, which sure enough is the exact same answer that we got from using Heron's area formula. Okay, so either way, Heron's area formula is the only way we're going to be able to solve for the area of a triangle if all we're given are all three sides of the triangle.